So, part 2. This is the second paper. I misspoke. It wasn't broken into 2 parts. It's broken into 2 parts on the version that I'm looking at. This is the Springer Nature formatting, where it's not double columns, so I can read the paper better. All right, so moving on. This is video number 2. My name's Joe. People call me Mr. Mellon. It's a pleasure to make your acquaintance. And Ho Aeon Mellon. May peace be with you. And so this is the mechanical substrate and the Higgs yield point. This is ultimately going to turn into, remember when I said that you're going to be able to do the math? I understand a lot of this complex math you're probably not going to be able to do. You're going to be able to do the step that I did and what I noticed, and we're going to cover that here. So first off, the introduction to it, space, it has a capacity. All right, it cuts off at a specific point because of the nature of the material itself. There's a mechanical limit to it. That's why we see black holes in the first place, because space fills up. So the easiest way that I describe black holes now, they're space particles. They're just made of pure space. Pretty much pure energy, but it's compacted, and it's the fundamental parts of space itself, the geometries that are compacted together. Ultimately, space just fills up, and then it overflows to the next space around them. But section 17 defines the actual mechanical limit. Section 17.1 goes over the basic fundamental postulate of QSM. The standard general relativity assumes that the gravitational coupling is a fundamental constant, but QSM posits that G is an emergent property of the vacuum's mechanical stiffness. And then it shows the stiffness relation equation. The rigidity of space-time is directly proportional to the self-coupling strength of the Higgs field. When it reaches 0 at the yield point, its stiffness becomes 0, which it causes the gravitational coupling to diverge or saturate, and leading to a plastic flow. It fills up, and then the space around it acts more in accordance with momentum space than it does with our 4D experience. It produces the origin of gravity, though, because it ultimately distorts space as we see it and creates that expansion that we see that is described by relativity in most places. We go through the mathematical derivation of the yield point. We use it in a real-world calculation here. We give you an analogy to kind of visualize the concept. We compared the vacuum manifold to a structural material, such as high-strength steel. You know, below the limit, the vacuum fluctuations are stored as elastic potential energy. That's the standard model, general relativity. The plastic regime, above a certain limit, the vacuum lattice cannot store that potential energy, so it undergoes plastic flow. It goes around, it starts to spread out. We go through the evolution of the field equation, starting with stage 1, special relativity, flat space. Stage 2, general relativity, curved space. And then stage 3, the violation of the balancing principle, which is what happened when they added lambda. They didn't finish the inverse additive. That's the step that I saw. Once they did that, it violated the balancing principle of differential equations, which states that any operation performed on one side must be mirrored by its inverse on the other side. Standard theory added energy plus, without the corresponding subtractive mechanism on the other side, it ignores the quantum mechanical requirement of the additive inverse. That's algebra 1. I took it twice in 2 different schools and passed both times in high school. But that particular thing right there really explains the rest of the paper and how we then have to derive from that. So that other math, if it's too much for you, I get it. We can stick to that's all great and beautiful stuff, as Feynman said. The shut up and calculate can be on the paperwork, and those who are adept with it can feel free to go through it. And like I said, we'll make videos with it. I'll use the AI and I'll have it broken down step by step, and we'll just go over some of that stuff in the future once we get all this information out there, and people can start looking through it and doing it for themselves and trying to figure out where it's wrong. So next is the fermionic subtraction. This is kind of the balancing act for lambda. Ultimately, lambda, it's not necessary. All of those terms go into one, and the differential is what really explains the expansion after the start. But we go through the math on that. It shows the boundary condition. Now, prior to the discovery of the Higgs, physics lacked the variable necessary to define the structural limit of the container. The top quark at 173 gigaelectron volts provides a massive negative contribution, -1, that pulls against the Higgs field's positive potential, creating a net zero coupling at lambda QSM. So the inverse additive, that's where it ends up just kind of cutting off. It just can't, space can no longer take any more there, and it disperses it in a different angle. It becomes saturated. It's a physical cutoff for reality based on the parts. We go through the saturation function with that, the string effective action corrections. That's the next section on that. The failure of the perturbative truncation. Prior attempts to utilize these terms, such as effective field theory, have historically failed to cure singularities because they rely on truncation. So once you understand the parts, you don't need to do that. Space really does, based on what we see, have a finite cutoff. It has properties to it. We are not taking those into account. This information here is. They end up failing because they treated an infinite geometric series as a finite polynomial, but we resolve this by demanding a non-perturbative resummation of the entire series. So the properties end up coming into play. It's important. Section 19, 3, fundamental QSM Lagrangian. So that's for it shows how that math is specifically negotiated. The saturation equation of state is next. It shows the historical precedent, the Bohr infield electrodynamics. Okay, ultimately we can derive electromagnetism from the same information. Maxwell's equations, all that stuff comes through the same way. So I'm really just finishing math that is correct, partly. So I'm just topping it off and showing how they're all connected. So, but yes, Maxwell's equations predict that self-energy of a point electron is infinite because of the electric field diverges. But the solution, the Bohr infield modified the Lagrangian density by producing a critical field limit. So we have precedents for this. It has been done before. Now, this leads into the origin of the 120 order of magnitude error when we initially calculated what was it? The observed density, and the reason why lambda's expansion is what it is. So what we can do now is see why that number was an error at all. The largest, mismatch in physics, but we could see what they overlooked to make that happen. Standard QFT integrates a zero-point energy modes up into the Planck mass, assuming the vacuum is infinitely elastic until gravity becomes quantum. Standard physics assumes that the vacuum would not break until 10 to the 19th giga-electron volts, but QSM identifies that the rod actually breaks at the scale of 10 to the 11th giga-electron volts. And failing to account for the material yield point of the vacuum, physicists overestimated the stored potential capacity of the universe by 32 orders of magnitude, from 10 to the 76th to 10 to the 44th, which it's huge. It's an order of magnitude of 120 once you expand it out to the whole thing. So it's like, you know, why did that happen? We don't see that in experiments. There's a universal ceiling. That's section 19.7. We can now rigorously calculate the behavior of the metric at the singularity, it taking into account the limits as the stress tensor goes into infinity. It really, again, now that we've got that final step to general relativity, it shows where that math ends up going in general relativity's equations. It resolves the vacuum energy discrepancy. We apply the limit to the calculations of the zero-point energy density, demonstrating how the saturation mechanism resolves the calculation deficit, and it relates to modern observations. So we have examples of that in here. Section 20.2, the equation of state for the plastic flow. It shows what happens when you get to that saturation limit and how to calculate that. Section 20.3, microscopic derivation of the vacuum viscosity. That shows how that bulk viscosity moves. The density yielded Planck volumes per unit of volume scale with the cubic yield scale. So all of those equations are there when we go through the math step by step. Section 20, decoupling static tension from a dynamic pressure. Now, the container, the immense energies of the bosons and fermions define the structural integrity of the vacuum in those locations. Because this confining pressure is uniform and constant, it decouples from the curvature evolution equations in the unimodular gravity. The gravitational field couples strictly to the stress gradients, not the absolute magnitude of the background potential. So and in part 2, it goes into the dynamic pressure, the friction. The observed parameter of lambda corresponds strictly to the viscous dissipation. This energy exists only because the universe is expanding against the vacuum substrate. And thus, lambda, it's not the sum of particles, it's the thermodynamic work done against the medium by the constituent parts. So that right there shows why galaxies and everything else, they end up ultimately being able to be explained through a dynamic environment. We're in a sea of space. It's kind of funny. They've been saying that for how long, that we live in a sea of space or an ocean of space, and it's pretty much true. They just didn't understand what the fluid of the sea was made of. So, back to the paper, section 20.5, gravitational decoupling via a unimodular theory. Why does the immense static tension not cause the universe to collapse? The resolution lies in the specific coupling of the vacuum energy to space-time curvature. And it goes into the yield point, the boundary conditions, and the physical constraints of the system itself. They have experimental information that we've already found showing this. Section 21 goes over some of that. The top quark and the geometric saturation point. We show that the standard model has no mechanism to explain the hierarchy of fermion masses, nor why the spectrum abruptly terminates at the top quark of 173 giga electron volts. Now, we derived that this upper bound is a geometric saturation of the vacuum interaction. And then we go in for section 21, 1.1, 1.2, 1.3, and explain all that. 1.4, 1.5. Yeah, and because of the shape of space itself, there's going to be a zone that is and not angled correctly, so to say, to sum it up. And so we explain why there's that desert there compared to the Higgs itself. And section 1.6, refutation of geometric stabilization models. Theoretical, we go over different theoretical proposals and kind of explain why they don't take the whole picture into account. Section 21.2, we go more into depth on the Hubble tension and how to resolve that and why there's an intrinsic speed limit. Section 21.3, the vacuum bifringe and the gravitational analogy. So we go over, it says, to address the extension of the vacuum bifringe to the gravitational sector within the quantum space mechanism framework, we must bridge the gap between electrodynamic stress, Heisenberg-Euler, and gravitational metric saturation. In the QSM, the vacuum is treated as a material medium with a yield point. The following derivation demonstrates how gravitational stress leads to metric saturation in a manner analogous to optical bifringe. So it distorts space, and the matter inside that space follows that trajectory. But we go into that further for section 3.1, 2, 3, 4, and so yes, it mathematically confirms that the vacuum processes material properties, specifically a variable stiffness that prevents singularities by saturating the metric response at the Higgs scale. Space can only hold so much. You can't overfill a cup of coffee. You know, I can try. What's going to happen when I take this cup of coffee and put more coffee in it than it can hold? It spills. Oh, it spills over. Space is just like that. And that's a property that we've been overlooking. This paper shows why we can't really overlook that. And looking back on it, it just has to be updated. That's all. Section 22.2, the vacuum energy partitioning, goes over what happens there with that dynamic process. Section 223 is metric hysteresis and fermionic coupling, the role of the top quark and the stability boundary. We go into that in more depth. Section 23, we have implications for applied physics. And then we go through that whole section, and vacuum energy extraction, metric engineering, EM coupling, variable stiffness of space-time. Eventually it's going to lead to easier transport. Section 23.31, it gives you some of the math for that to show how we can pull energy from the pressure of space itself that we're already in. So that pretty much means that eventually we could just run all of our vehicles, all of our electronics off of the intrinsic volume of pressure that we are surrounded by with space. And it's not exactly infinite energy because it requires the rest of the universe as well. But for our purposes and the amount of energy we're going to be pulling from it is nothing. It's a little drop it's a thimble in an ocean. So that's not something we're necessarily going to have to worry about running out. And so again, it seems like it's infinite energy. People say, oh, it's infinite energy, this and that. No, it's got structure to it. You have to know how to manipulate it. And yes, if you're pulling energy from it, it's coming from the outside of space. So ultimately it's coming from the ocean itself. And you're shifting that energy around that's already present. So it's not infinite, it's there, it's accounted for, and there is changes down to the overall volume of the universe, but we are very tiny in the scale of things there. Next, on section 24, we go to falsification avenues. So if we see different things, it would mean that this theory is wrong. So if, for instance, if we see another generation above the top quark, obviously this is going to end up being wrong. But if that happens, also the standard model is going to be wrong, as well as a whole bunch of other stuff. So either way, if we have a fourth generation of heavy fermion, great. We'll see where that goes. Section 24.2, certain noises. If we hear a certain background noise with LISA, the Einstein telescope, and future gravitational wave observatories and stuff like that, there's going to be a way that we can tell if this thing is wrong. Section 24.3, high intensity fields, extreme magnetic fields. Experiments using high intensity laser interactions to test the vacuum bifurence must also show deviations from the Heisenberg-Euler linearity at high energy densities. A null result in the strong field gravity test where G remains constant despite these other terms. It would refute the softening function. So again, if you have the resources to try to prove this thing wrong, feel free. I dare you. Section 25 is the conclusion. So we go over again the worst prediction in physics, how this thing solves it, and that's it for paper number 2. I appreciate you guys watching. Stay tuned. And again, ho, Aeon, Melon, and may peace be with you.